My fear is that there was some teacher who said, "Oh, that's really good. Why don't you post it?" Oh, I hope not. Maybe the teacher looked at it and said, "That's a complete piece of crap. You don't understand what's going on. Remove it immediately." As opposed to, "Hey, demonstrate your ignorance to the world." I try to minimize the ignorance, which is probably why I should delete all of these videos. All right, questions at the moment? Originally, I wasn't planning to do this at this point, but it just sort of came up. All right, so let's actually work through the process here. We'll start out on a simple example, and then we will move from there. I think that's where I started, so we'll start erasing there. All right, so we will take put the earth down here. So I have some cliff or table or whatever you want it to be. I have an ideal pulley. I have a box sitting up here, a rope, and a mast dangling. For our first example of going through this, let's make the assumption that we are dealing with a frictionless surface here, and I'm just going to symbolize frictionless with the shorthand of a mu equals 0. Mu is a symbol to represent the coefficient of friction. So it is a mu, and it's the coefficient of friction. We will talk about that in more detail probably today. Let's come up with a mass here. So well, let's make this a 10 kilogram mass and 5 kilograms. Earth. Now, when I wrote down 10 kilogram mass, I specifically said, let's make it a 10 kilogram mass. If I had said instead it's a 10 kilogram box, what's the big clue to tell you that that's the mass?
Calling the mass?
No, if I didn't, if I just said it was a 10 kilogram box, how would you know that that is the mass? Say it like you mean it.
Kilogram.
Yes, units. What is the weight of the box? Hint, it's not 10 kilograms. The weight of the box. And this is the biggest issue I have. Most of you have done life science classes where they use kilograms as a unit of weight. Next time a biology person does that, a life science person does that, look at them with a withering glare and tell them, no, kilograms is not a unit of weight. It's a unit of mass. So be harsher if you need to be.
It depends on the force of gravity or acceleration of gravity on that particular planet that they're on.
Yes, it would. I could take a 10 kilogram box here, put it on the moon. It has the exact same mass. It definitely does not have the same weight. Now, one of the reasons why I think the life science people don't use them, why they use them interchangeably is the fact that they only deal with things on Earth. It's physics. We cannot do that. We cannot make the assumption that everything that we do is for things that are stuck here on Earth. Now, the relationship between weight and mass we will get to. They are related. All right, so first diagram. Since we are still early on in the process, I will draw more than we actually need to solve the problem. We got our checklist. Not F-pound, F-tom. All right, so what do we know?
Normal force.
Acting which way on what?
Left box between the ground and
Okay, acting which way on the box? So I have a normal force here. I'm going to, since I don't have any other label for it, I'm just do it y sub 10, just to represent it's the 10 kilogram box.
down.
Y sub 10. Wow, Newton's the wrong action.
And you said the pulley is
The pulley and the rope are both ideal.
what does that mean?
The ideal pulley, let me do it over here. The ideal pulley has two major characteristics. Frictionless and massless. Although, if it's frictionless, then it really doesn't matter if it's mass or not, it's not moving. And then the ideal rope. Frictionless. So that rope's just going to slide over this. This is just, I could have equally just drawn a part of the ground to sort of jut it out, as opposed to it has to be a pulley. Frictionless, massless, and stretchless. The stretchless piece is, I don't want it so that the 5 kilogram mass could be moving while the 10 kilogram mass is staying behind. Like the Slinky Dog in Toy Story. At some point we will add friction to them, and we'll add mass to the pulley. That's later on. All right, any other normal forces?
Oh. The 5 killer box, it'll be Y go up when Y go down.
It's not switching it.
Oh, it's not. Oh, never mind.
The pulley in the rope?
Yep, that's the other one. So Y sub R, Y sub R. There's got to be something causing the rope to bend like that. All right. No, we have, so in terms of contact, we have contact there, we have contact here. This isn't touching anything other than the rope, but that's not normal force. We're done with normal force, done. All right, what next? Questions?
Yeah. So the contact. So because it's not like a hill that's like that, and the Y is like that way. If you remember from last class.
Oh, if it's around, because the normal force is always perpendicular to the surfaces, and since these surfaces are horizontal, the normal forces will be perpendicular here. Will be vertical.
Okay. So W wouldn't be going that way, right?
Normal force would not be going that way on these.
Okay. Okay.
If this mass were touching the side of the hill here, then there'd be a normal force that's acting left and right here. But normal, again, is a math term meaning perpendicular.
Yeah.
Other forces? Somebody said it right before the question.
Gravitational weights. Oh, you're not there yet.
No, we're there.
Okay.
So weight.
10 kilogram box on the ground.
All right. So which way am I drawing this on the box, or which way am I drawing it on the ground?
It should be up on the ground, it should be down on the box.
All right. I think that's what you said, right, Junior? All right, so up on the ground, down on the box. All right. W sub 10 and W sub 10.
So will it always be W, or like can we have a place where we just declare our variables, like this is what this is?
If you want to declare your variables, that's fine.
Okay.
Same thing about the 5 killer. Force go down.
So, W sub 5, W sub 5, or, yeah, 5. Those are the only two things with mass besides the planet, but that's the planet's the reason why there is a gravitational force. So gravitational force, done. Next.
There's tension between
the rope and the 5 kilogram box, and the arrow should be on the rope, should be pointing down,
Like that? That's what you're saying?
and then up on the box.
Yeah. The tension's what's holding the box up. And it's also what's making the rope tight.
I have a question. What does O mean again?
Other.
Could we eliminate it?
Yes, we can. When would other show up?
Pushing,
There's like a strange other force that we're not taking into consideration or not. No, it's vague, but
When the source is
source, yeah.
either unknown or academically we don't care about it. Typically, textbook problems are full of others. At 5 Newton force is pushing on a box. What's causing 5 Newton force? I don't know. That's another. And we've got another pair of tensions.
Right on the other side.
Yep. A rope's going to have a tension at each end. FD here, FD here. Now, when we did the force diagram, the complex force diagrams, I said that we can, if you're doing subscripts, these two right here need to have the same subscript, and these two here right here need to have the same subscript. And if you put the subscripts here for the force diagram piece, it's not wrong. But when we actually come to solving for acceleration, I didn't actually state that, so the acceleration is equal to what? When we solve for the acceleration, at some point we do need to acknowledge that because of the ideal nature, these tensions are the same. Otherwise, it's not solvable without more information. All right, so that's tension. And what about friction?
10 kilogram box in the ground.
Why not?
Box. Oh,
Is there a 5 kilogram box in the ground?
Because you declared friction 0.
Yes.
oh, you forgot about that.
Ordinarily, yes, absolutely. There would be friction between the box and the ground. Which way would, if there were friction, which way would friction act on the box?
That to the
Yeah. Because the box wants to move that way relative to the ground, therefore the friction opposes that and says, no, I'm not going to let you. And oftentimes friction is not strong enough to be able to back up its claim or its threat. So, but in this case, it's in the problem. All right, so we're done with the force diagram. Done. And I know what you're thinking, because I would be thinking the exact same thing in your spot. You're thinking, hey, that's great, but where's the math? We're getting to it. All right, so next thing, acceleration, the direction. Which way is the 10 kilogram box going to accelerate? I wasn't which way were you pointing, Rodrigo? You're going that way? Anyone else?
I agree.
You agree? And whether you're pointing at Rodrigo or pointing in the direction of acceleration, you're right either way. This will accelerate that way. Which way will this box accelerate? Changing your mind? Which way is it going to accelerate?
Downward.
Yeah. If they accelerated, if the 10 kilograms accelerated to the right and the 5 kilogram accelerated upwards, there wouldn't be any tension in the rope, as well as magic would be afoot. So now we set up our coordinate axes.
It's 10 kilo, whatever be stationary. It's the higher number is not.
There's nothing to hold this back. This box is going to accelerate.
Okay.
It's not going to go into the ground or come off the ground, so these two forces will balance each other out. And there's nothing to counter this force right here. So that 10 kilogram box will accelerate to the right. And if it's accelerating to the right, this better be accelerating downwards. Otherwise, something strange. Nobel Prize? Perhaps.
Automatic A.
Second?
Automatic A.
All sorts of good things would come from it. Or the destruction of all civilization because the laws of physics no longer apply. Silly. All right, so we have the directions of acceleration. That's done. Coordinate axes. We have two different masses in play here. What I care about is this mass right here, and I care about this mass right here. I don't care about the ground in terms of doing the analysis, because I'm asking about what is the acceleration of the masses. So that's what I care about. The rope is massless, so it's hard to plug a massless object in F equals ma. So, coordinate axes. Usually, you want one of the axes to be in the direction of acceleration. And when we get to the equations, I'll re-emphasize why that makes life a whole lot nicer. So, I'm going to make one of my axes for this one right here. I'm going to call that I hat 10, in the same direction as acceleration. There are times in which you want the direction of the coordinate axis to be in the direction of movement or velocity. We'll get to a case like that later. And the j hat direction is just perpendicular to it. I don't care if it's up or down.
Down.
Down? Okay. Call that the j10 hat. And over here, since acceleration is down, since I have this in the direction of acceleration, it's helpful to have the same over here, this in direction of acceleration, and I'm going to call it a I5 hat, or you could do a J5 hat, doesn't really matter. I could have throw in a J hat, since I did I hat here, I could do a J hat either going left or right, but there are no forces in that direction, and so if we did that, ultimately, we'd end up with an equation of 0 equals 0, which, although true, is not really helpful. Coordinate axes, done. Decomposition. When you get to the decompose phase, are there any forces acting on the 10 kilogram box that are not in the positive or negative I direction or positive or negative j direction?
No.
So nothing to decompose there. Are there any forces here that are not in the plus or minus I5 hat direction? Nothing to decompose there. So decomposition we don't have to do in this particular example. We'll save that for the next one. Equations of motion. F equals ma is our starting point. How many equations will we have?
A lot.
I want to say 15, just to guess.
Wow, if we had to do 15 equations,
It's probably 3.
we probably would spend the first month working on computer skills. What was your probability?
Maybe 3 or 2.
Anyone want to say anything with confidence here?
5. 1. We have acceleration.
You got force, acceleration, that's 2.
How many directions do we have here?
2.
How many do we have here?
1.
That makes 3. So congratulations to the person who said 3. I heard it back there. So we're going to have an I10 hat direction, a equation, a J10 equation, and an I5 hat equation. Those are the 3 equations we're going to have. The way you do them. Some students find it very difficult, but it actually, relax, it's not complicated. Let's take the I10 hat direction equation. I10 hat is to the right. So we look at this mass right here. What are all the forces in the positive I10 hat direction? Because we've already done the force diagram, what are all the forces in the positive I10 hat? I know people are speaking, but I'm not hearing anything distinct.
Acceleration.
Not a force.
1.
Tension.
What are all the forces? Thank you, Samaya.
Tension.
Samya, apologies.
No.
Tension, so I write down tension. Minus. What are all the forces in the negative I10 hat direction? None. So I don't have that. Equals. mass of the 10 kilogram times the acceleration.
Is that A0?
No, I labeled the acceleration A.
Oh, okay.
So it is in the positive direction, and so that's why this is positive. And A is just the magnitude. All right, the J10. What are all the forces in the positive J10 hat direction?
Gravity. Gravity. Or weight, sorry.
All right, so we write down weight. What are all the ones in the negative direction?
Normal.
Any other forces? In that direction on that mass? Equals the mass of that times, what is the acceleration in that direction? Height? Louder?
None.
None. Oh, okay. Or 0. And this is why we chose our coordinate axes the way we did. I want one of the equations to be equal to 0. If you choose a coordinate system such that one of the equations is not 0, you are probably quadrupling the amount of math you have to do. As you get into more and more sophisticated physics, a lot of time is spent trying to find a coordinate system to minimize the amount of math you have to do. Because remember, all this was developed prior to any sort of electronic computations, and so they are trying to find shorter ways of doing it. Also, all right, so the I5, what would this equation be?
Weight. Minus the force of tension. Equals the mass.
5.
That's 5. So what's that over here?
Acceleration.
No.
Minus
Acceleration.
Yeah, times acceleration. The acceleration is 9.8 only if it's in free fall. It's not in free fall.
So why is it minus tension?
Because we said that downward is positive.
That's right.
That's why I have the steps laid out. Once we have if we do the force diagram right and we have the coordinate axes laid out, then this part right here should be just, oh, positive that way. It's that minus that. And now. Oh, that's it for the awareness equation. Substitution. What I mean by substitution, oh, any other questions before we do substitution?
So, never mind, you answered it. Because if A was going the other way, it'll be negative A.
Right, if we had chosen up to be positive,
Yeah.
acceleration is still down, but if we had chosen up to be positive, then it'd be tension minus this weight is equal to negative mass times acceleration.
Okay.
All right, substitution. I'm looking at these things, and the question is do we have an independent formula for any of these? There's not an independent formula for tension. Tension always depends upon the problem. Normal force always depends upon the problem. Weight does not depend on the problem. So we just do a little sidebar over here. If I have an object in free fall, what are all the forces acting on it if it's in free fall? Or force due to gravity, or weight. All right, that's it. If I plug in F equals ma, I have weight is equal to the mass times, well, if it's in free fall, the acceleration is the acceleration due to gravity. There's your formula for weight. So anywhere I have weight in here, I can now write this. So my three equations are, the first one doesn't change at all. Tension is equal to mass 10 times A. Second one, I have M10G minus Y10 is equal to 0. And then M5G minus the tension is equal to M5A.
Second one.
That's a 0 there. Is that part? Now this middle equation with the normal force in it, without friction, it really just not going to have any impact in this particular problem. If we had friction, it would matter, but it doesn't. So all I really care about are these two equations here. Again, I'm solving for acceleration. Those are the equations with acceleration. To solve it, I'm just going to add the two equations together. I'm going to add the left sides and add the right sides. Another advantage of picking our coordinate system the way we did is that when I add these two together, the tension is going to cancel out. Tension does not, whatever the tension is, we don't need to know it. Add them together, and I'm left with M5G. And this negative tension cancels out with that positive tension. And on the right-hand side, I have M10A plus M5A.
What about the normal force? The Y2?
I actually don't need this equation for this problem. So later on, this will have greater impact, but at the moment it is not. So M5G equals M10 plus M5 times A, factoring A out. And again, we're trying to find the acceleration, so let's shoot over here. Acceleration, therefore, is M5G divided by M10 plus M5. We have a formula for acceleration for this problem. It's now a plug and chug problem. 5 times 9.8 divided by 10 plus 5, which ends up being, that's 49 divided by 15, which is 3 and 4/15, which in decimal form is 3.26.
2 seconds. Meters per second squared.
Yeah. Meters per second squared. And we've gone through the process now. At this point, it's just variations on a theme. Questions? And again, I know what you're thinking. The math was great, but can you make it more exciting than 2 boxes in a cliff? Oh, yeah. Box on ramp. I'm about to start racing. Anyone need me to pause for a moment before I start racing? So angle theta. Box on ramp of some mass m. I'm going to give you the mass, but ultimately, I've done this problem enough. The mass doesn't actually matter to the answer to the problem. Let's make it a 10 kilogram mass. We'll make this angle 57 degrees. And as with a lot of these problems, what is the acceleration? That's what's happening. The question is, what is the acceleration of the box? Now, the first time we go through this, we are going to simplify it just a little bit. I'm going to say friction is 0. So I'm going to say frictionless ramp. The ramp is attached to the ground, as indicated by the fact that I don't have a solid line down here, so we don't need to worry about the ramp getting kicked off to your left. Or kicked back to the left. Pardon?
No, that was it.
57 degrees.
57 degrees, yes.
And if that line at the bottom wasn't there, there would be an angle.
I put the line there to indicate the angle that's 57 degrees is between the ramp and what is supposed to be horizontal.
Okay.
If I officially, from my point of view, if I didn't do that, it becomes a little bit more nebulous about, okay, it's 57 degrees to what? From the ramp to something. And I was just trying to indicate to that level surface there. Now it looks like the box and the damaged shark fin. All right. Any questions before we start on the force diagram? In a world where boxes are made to sit on ramps. All right, so what are the forces? Let's put up our checklist here.
I can get rid of other and friction.
And tension. The normal force between the box and the ramp.
Which way is the normal force going on the box? So I got people pointing in all sorts of directions here. It is indeed perpendicular. It's perpendicular to, that's the surface of contact. It has to be perpendicular to that. It's up and to the right, given my drawing. So that's the only, I have only two objects. There's contact between them, so there's a normal force. And gravitational force?
On the bottom, this one. On the floor. That one, yeah.
Which way is it acting on the floor?
Up.
Okay.
And then down.
I assume on the box, you mean? So I have only two forces acting on the box.